All right, so today we are talking about trigonometric functions. This was a very fast unit, so hopefully it's a very fast study guide day as well as our problem set. So I wanted to start off with just reminding us about radians. Radians are just another way to measure angles or rotation. Normally we see degrees. Radians are just another way to do that. And the key takeaway here, it is directly tied to our arc length. If we take that radius and we wrap that radius around our circle and create an arc there, okay, that angle that's made, that gives us 1 radian. So that might come up as a question just based on the definition of what a radian is. So be mindful of that. And remember that pi radians, or halfway around our circle, is 180 degrees, or consequently 2 pi and 360 line up as well. That pi and 180 is the best way to kind of remember our conversion between radians and degrees. If I'm taking radians and converting into degrees, I'm going to take 180, multiply it with the radians, and then divide by pi. The best way to remember this is this pi is going to cancel out the pi that's included in our radian measure and going to give us a nice clean number for degrees. So let's remember how we do this. I'm going to set up my equation. Degrees equals, my radian measure is 2 pi over 3, multiplying with 180 over pi. Notice this 180 over pi is always going to be there. And then we can multiply straight across. And before we even do that, we might notice that, hey, there's a pi on top, there's a pi on bottom. So I can cancel those out, and I'm just left with 2 times 180 over 3. If you want to do that mental math, you are more than welcome to. We'll get 120 degrees. However, I recommend, let's just use Desmos to get that figured out. So 2 times 180, and that is divided by 3. That gives us that 120 that we talked about. But similarly, we could have taken this original formula set up here before crossing stuff out. We could have typed that in and gotten the same thing. I set up my fraction. I got 2 pi over 3 times 180 over pi. And you'll notice that we get the same exact answers there, however we set it up. That's just because those pi's cancel out. Working the other direction, we want to get pi back into our unit of measurement, since radians are typically in terms of pi. So that fraction is just flipped. We're multiplying by pi, dividing by 180. So I'm going to set this problem up with 150 degrees. Radians equals 150 times pi over 180. And we probably want to rewrite that as a fraction right off the bat too. 150 pi over 180. And then notice how the way this question is phrased, we want to write our answer in terms of pi and as a decimal. So even though we can plug this in right away, if we wanted to get 150 pi over 180 and see that we get 2.62, we also want to kind of write a simplified fraction in terms of pi. So what we can do then is kind of divide out numbers that work in the top and bottom. I can divide out 10 from the top and bottom, so I get 15 pi over 18. This was a divide by 10. In my next step here, it looks like I can divide out 5 to get 3 pi over, I can't divide out 5, sorry. I can divide out a 3 to get 5 pi over 6, and that gives me that final answer there. So 5 pi over 6, let's just double check, see if that gets us the same thing our original did. 5 pi over 6, boom, 2.62. And so if we want to write our answer in terms of pi and as a decimal, we can go or 2.62 radians. So degrees and radians measure rotation, and the thing we mainly talked about rotating around was our unit circle. This unit circle has a radius of 1. Cosine kind of tracks that co-height around the unit circle. Sine tracks that height around the unit circle. If we go back to that GeoGebra tool, which you can still access on Canvas, remember that that triangle changes shape as we go, and that width and height change shape with it. As we move around the unit circle, sine is going to describe the height as we move around that unit circle, and that's going to associate with the y coordinate. Cosine is going to describe the co-height. That's that side-to-side motion, co-height there, and that's going to be our x coordinate as we move around. These are programmed into our calculator and into Desmos, but we need to make sure that our angles are in the right units. That's the most important thing. So unless you see that degree symbol, default to radians unless you're told otherwise. So we can take example 3. We can evaluate all 4 of these really fast. First thing I'm going to do is make sure that I'm in radians. Close this out. And so for A, I have cosine of pi over 6. So I literally just need to type that in. Pi divided by 6. Cosine of pi divided by 6. And I get 0.87 if I'm rounding to the nearest hundredth. Okay, moving on to B, I have sine of 314. Notice how this is in degrees. So I'm going to type that in as sine of 314. And notice how it gives me one thing here. But if I change my unit to degrees, which we should be in here, notice how both my answers change, the problem A and part B. So we got to make sure our units are correct. So in this case, sine of 314, we get negative 0.72. Then we get cosine of negative 130. That's also in degrees. So I'm going to just leave that as is because my units are already in degrees there. Negative 0.64. And lastly, sine of 11 pi over 6. We don't have the degree symbol, so we should go back to radians. Let me just again reiterate how easy it is to get the wrong thing. If I just type it in, it gives me this number, but hey, that's our degrees input. We want this to be a radian input, gives us a very different answer with negative 0.5. And that should be a negative sign out in front. So there's not a lot to cover here. So I left some doodle space in the front because I couldn't fit everything on the in that space I needed. So I wanted to keep these sine and cosine graphs together, which is now on the back side of your sheet. So especially with these, make sure that your default setting is radians. If you graph stuff in degrees, which I'll do right here, when I go sine of x, we're just going to get this really like elongated line, and it takes a really far zoom out to even see any sort of wave on it. So make sure just starting off with our radians so we can get that sine wave. So these waveforms kind of map that rotation around the circle of our triangle, the height and co-height as it rotates around. So it's just going to repeat over and over again. And there's 3 features that show up. We have midline, we have an amplitude, and a period. All of these can be found from our equation, regardless of whether we're using the sine or the cosine function. Amplitude is just that number out in front. It's what we're multiplying by. B changes the period. Notice how it's not the period. It's used to calculate the period. And that vertical shift, that thing that we add at the end, plus D, that's going to be where our midline is. So if I'm using example 4 here, I should be able to find everything just from this equation. My amplitude should be 5 because that 5 is out in front. The equation of that midline, that's the thing at the end here, is negative 4. So we'll have y equals negative 4. That's our shift. And then to find the period, I need to find what B is. So 6 is B. B equals 6. And so that period is going to be 2 pi divided by B, which is 6. And we can just write that in simpler form then as pi over 3 in order to get that period. So let me just double check this in Desmos real fast, just to confirm that this equation matches our graph. We get 5 cosine of 6x minus 4. And if I kind of zoom down here, I'm going to throw my midline on here that we said it was y equals negative 4, just to visualize it. We're saying that our midline's at our red line, and if I look, it seems like it cuts that in half perfectly. I can count up from the midline 1, 2, 3, 4, 5 spaces, or down 1, 2, 3, 4, 5 spaces. Additionally, we can kind of trace our period, and this goes from one full rotation. So starting at a max point here, if I trace down, up back through my midline, and back to the top, looks like that happens at x equals pi over 3. Boom, that's exactly what our period was pi over 3. So we can also identify this stuff from our graphs if we need to. So I'm given the graph here as shown. I'm looking for the midline, the amplitude, and the period. Midline is always the first thing I'd recommend finding, and I'd recommend finding it just by trying to find um, that line of symmetry. And let's say I get it wrong at first and I place it at -3. Well, if I draw that across, this distance is so much bigger than this distance. Very clearly did not find the line of symmetry there. So I got to shift it up a bit. It looks like that line of symmetry is at -2. So that tells me that that equation of the midline is y equals -2. Then if I want to find the amplitude, I just need to count up from the midline to one of my peaks. And it looks like if I do that, I have 1 space, 2 space, 3 spaces. That should be the same if I were to count down to one of my peaks. From -2, I got 1, 2, 3 spaces. So my amplitude is 3. And if for whatever reason we count and we get different amplitudes, that means we did not find the midline correctly. Last one is period, and this is it looks like a sine function, so it's going to kind of start at the midline here. If you notice that, hey, our starting point is at that -2. If I trace one full rotation around, go up, go down, back to center, okay, that lines up with 2 pi. So my period here is just 2 pi. There's nothing we need to do in terms of 2 pi divided by anything. The period from the graph is just as written on the graph. Let's keep talking about period as we go into example 6, though, because this looks a little bit differently. Notice how my graph here starts at a minimum point. So I need to go through my midline all the way up and back down and back to center. I don't need to pass it twice here because I've already gone through one full rotation right here, which means my period is at pi. So through that, I kind of already found where the midline is at. I traced it with that purple line there. It looks like it's at a value of 2. So our midline, our equation of the midline is going to be y equals 2. Oops. And then so that amplitude there, if I measure from the midline to a peak, I only go up 1 space. I only go down 1 space. So our amplitude is simply going to be